Hello, I'm Walt. So this talk was originally going to be given by my colleague John Davis. Unfortunately for all of you, because he's a really great speaker, he left us to go work at Facebook and is busy learning how to Facebook right now. So you're stuck with me. Sorry about that. So I work at Civis Analytics, which is a data science company. We do predictions and inference on individual level behaviors. We have offices in Chicago and DC. If you would like to work for them, that would be cool. I myself work out of our Oakland office, which is my apartment. The only other person who works there is my cat, who is currently she's learning SQL right now. It's going okay. So this is the beginning of the slides that I actually made. Our PR department did a great job, but I don't really know how to use PowerPoint. So this is like, hey, I'm Walt, let's talk about dimensionality reduction. So the questions we're going to try to answer is, why would you want to do this dimension reduction thing? Once you've started doing it, how do you tell if it's working or not? And then once you are really on board with it, how do you scale it up? And so just to make sure we are all on the same page, what is dimension reduction? Let's say that we have some covariates X that we want to use to predict some response Y. So we want some transform T that after we apply it to X, we will get a much smaller X. And hopefully what will happen is if we have some evaluation metric F, the evaluation metric we apply to our model, when it is trained on either the transformed or untransformed data, it will hopefully work just as well. So that's it in kind of math. This is it in a cute picture. We want to take a big wide X, get a much smaller X, and then be a happy person when we build our models. So that's what we're shooting for. So why would we want to do this in the first place? Why do we want to build this skinnier X? The first is for speed. If we have a smaller amount of data, if nothing else, just the I/O to move around in and out of our database will be a lot faster. We'll save some time, but our predictions will run faster, our fitting will run faster, everything will run, of course, faster just because we have less stuff to work with. The other that we're going to talk about a little bit more, because I think it's maybe a little less obvious, is we can think about dimension reduction as a form of regularization. So if we look at this from kind of a social science perspective, let's imagine we have some treatment, like showing a person an advertisement for shoes, and we have some outcome that we're interested in, such as the person, did they go and buy shoes, yes or no? And so maybe they saw a really great ad, maybe they saw an ad that and there's oh, if I buy these shoes, I can slam dunk, and that's a thing I'm interested in my life. And they go and buy the ad, or they go and buy the shoes because of the ad. But we might also have some ancillary covariates which might also be related to the outcome. So if maybe they saw your ad, but they aren't buying the shoes because they saw your ad, they're buying the shoes because, their feet are on fire. Their shoes are literally on fire and they need to go buy some shoes. That is another reason, it might not be your ad. So then if we didn't attribute it to those ancillary covariates, we would be overstating the effect of our treatment. There is a third possibility that we should also be concerned about, which is that our ancillary covariates might have what I'm going to refer to as a spurious correlation with the outcome. So if we imagine that in our sample, amongst these ancillary covariates, just due to random noise in the data, we just happen to have amongst the sampled set there is some sort of correlation with this outcome that we are interested in. If we were to sample a bit more, the noise might go away, but maybe we just can't do any more sampling, especially getting data on people can be tricky. So instead what we can do if we are reducing the dimensions, we have fewer of these covariates, it's less likely that we will have these kind of just random correlations that would steal from our treatment. And so that's one reason why we might be interested in this. So now that we are super convinced, we're all on board, dimensions, we hate them, let's get rid of them, let's make them smaller. How do we tell, is this working, how is this going? So this is the question we are trying to answer, this evaluation metric that we have, AUC or whatever we decide to use. Once we apply our transform, how much does it go down? And so we are going to run some experiments. And so the most important thing that I'm going to recommend is keeping a strict wall between your configuration and your code. So here we're going to, in the code, is going to be defining the experimental design. So what actually happens in our experiment. So we're going to grab some data, we're going to apply this transform, fit a model, get some predictions, and then evaluate the out-of-sample scores. So that's what is actually happening, what is the design of our experiment. And so the config is going to state like a particular instance, a particular run of that experiment. So things like where is the data that we are evaluating, how many dimensions do we want to shrink to, what's the particular model, what's the particular transform. And so separating these things is nice. It's just kind of like good experimental design. It means it's not really possible to go and like think, oh, I'm just going to change the config, but actually change like the design of the experiment. If you keep a nice strong separation between the two. You can also just like check in your code, and then you have these really beautiful, in your version control, you have this beautiful history of how did like what is my experiment change over time, how did what I'm experimenting on, the experiments I run, it's all in version control, and it's all very lovely. And it's really easy to reproduce, if for instance, like you have a coworker who's going to go give a talk, and then that coworker leaves the company, and then they need to find someone else. Who knows? Anything like that could happen. It makes it really nice and easy to reproduce. And so for these experiments, we're going to target scikit-learn, which has a lovely logo. And so if you want to play along at home, which I recommend, you can find a lot of these things there in the random projection module, which is where a bunch of these things are, along with the manifold, so module implementing data embedding techniques. So we're producing smaller embeddings. Here's what we're doing. That's where most of these live. And so what we want to do is define some config that will allow us to take in an arbitrary scikit-learn transformer so that we can try them all. And so we can do this fairly easily because, like you're probably aware, Python's a dynamic language, but it's like a really dynamic language. So we're going to look at, our config is going to be in YAML. If you don't know what YAML is, it's kind of like hipster JSON. And we're going to look at some code which defines some runtime imports. So you might think of like imports, you've seen these things at the top of your program, maybe it seems like some magic part of Python. No, it turns out an import, just another function, you can call it runtime, just like any other function in Python. The same thing for attribute access. If you've done like array.shape or whatever to look up the shape attribute, looking up an attribute, just another function, you can call it runtime, just like anything else. So we see that here. This is the part of the talk where we look at screenshots of an Emacs session, which I'm sure you were all hoping would happen. So this is the config and the top left. So we're saying, okay, I want to import from scikit-learn. I want to import this thing called Gaussian random projection. And we should define a random state for this random projection to make this thing even more reproducible. So then in the bottom right, so we have to import the function, which does the import to do this. So we just want to import the thing named by our config. Get_attr is our like little secret. That is like the period. That is the attribute lookup that we can just do at runtime. Then we can get a class object and instantiate it. And this is how you write, like pretty simply in their little code. This is now config that will take anything, and obviously this works beyond scikit-learn. But that's kind of fun. So yeah, if you want to go like nuts, you can do crazy things in Python. Like if you want to say like pull a random number and depending on that random number change like the way addition works in Python, you can do that. It's a great idea if you're real tired of your job and you love burning bridges. Just slip that in there or something. You can get up to all sorts of no good. So we're going to look at some results. So this is going from 350 dimensions all the way down to just 10. And so we are going to look at the mean out of sample AUC on some doing cross validation over 5 folds. We're going to look at the mean of random forest and logistic regression. And so in the tables, pass-through refers to the original untransformed data. And so we're going to go over this really briefly because, time, and also because staring at tables together isn't like super fun, and if nothing, what else is this besides fun? And also because the point of this is not to be like, oh, the best thing is random projection. The point of this is to say, oh, like, run these experiments yourself. You should go and do this yourself. So if we look through this, so we see some examples, as you might expect, where we get the best result just on the untransformed data. We get some examples where we actually get like decent parity between the transformed and untransformed, and we get some where we actually see where some transformation techniques where we actually get slightly better AUC than we do on the untransformed data, which is kind of nuts. There might be something to this regularization idea, maybe. Anyway, so now that we are all really into this, we're all really excited, and we have a lot of data, and we want to try to do this at scale. So actually like fitting the transformer, we're not going to do in parallel, we're just going to like grab a random sample of our big data, like figuring out how to fit these transformers like in a distributed fashion is kind of a different question. But to the problem of like how do I apply this transform to a lot of data, that's the one we are going to take a crack at. And it turns out it's in the class of embarrassingly parallel problems. So embarrassingly parallel, so if we have like a couple million rows that we want to apply this transform to, we can apply it to like these 10,000 and these other 10,000, these other 10,000. We can do it completely independently. We don't require any sort of coordination like you would need in trickier parallelization problems. And so we're going to look at, and so yeah, just for reference, so it's kind of our workhorse database. It's 350 variables over 250 million folks. So I don't know, that's like maybe medium data. It's like big enough that you have to like think a bit about it. So if you're trying to do this, if you're trying to apply a transform over like these 250 million rows and just do it on your laptop, you're looking at like, it's like a day or at least a work day, and I don't like make overtime. So like we're not gonna do this. So instead of that, let's grab a dozen machines and we can get it down to something closer to like 2 hours here, which works with my schedule much better. And so we're gonna take a look at this using Spark. So Dask is something I would like to take a crack at for this kind of problem. I think Dask might be a better fit in some ways. But one of the reasons I tend to default to Spark myself is that at Civis we work on Amazon Web Services, and AWS has a kind of neat service called Elastic MapReduce EMR. So you can just say, hey, Amazon, I would like a cluster of like this many machines and this many cores each and this much memory. And they say, okay, I'll get back to you in 10 minutes. And then I go like play with my cat for 10 minutes. I quiz her, like what's the difference between an inner and outer join? And like we're getting closer. I think if she can like learn how to fizz buzz and learn how to like name drop Bloom filters every once in a while, she can totally pass an interview in the Bay Area and start pulling her weight. So that will be great. Anyway, so our 10 minutes is up. We've got our cluster. We run our experiments, flip the ops switch, and we are charged the nearest second for the amount of compute time we need. So for running ad hoc experiments like this, it's really handy and doesn't require me to like go talk to our systems team or anything like that, which is great because they're kind of tired of talking to me. So to take a very brief look at Spark and kind of its distributed processing, like how Spark looks at this. So it has a data frame abstraction. A data frame, of course, is a bunch of rows. And so Spark groups sections of these rows together in a thing it refers to as partitions. And so it will be, depending on the application, they will be different size, but just, you know, ballpark, it'll be like a few tens of thousands of rows in a single partition. And so this is kind of the nature. These partitions are the basis of its parallel computation. So it has a driver program that sits on the master node, and it says, okay, like you compute node, you're in charge of this partition, you're in charge of this one, you do this one. You might be familiar with this. If you are familiar with capitalism, you've probably encountered this line of organization. And so it gives you have two main primitives so we want to apply this transform to every single row in our database. It has just regular old map, you know, same as in Python. I'm sure you've encountered this, and it's just what it sounds like. We're applying this transform to every single row. It also allows you to work directly on the partitions themselves. So you can call map partition, and instead of taking in a single row, we are calling this once per partition. So we're calling this function we want to apply to the entire data set once with like chunks of these few tens of thousands of rows. And so working in chunks gives us a chance to make use of vectorized code. And so, like if we imagine we are doing, say, we're trying to apply random projection. So instead of doing that matrix multiplication, you know, just one single row at a time, we can grab these big chunks and do matrix multiplication on big arrays, which is how we're meant to do it, and make use of all that lovely vectorization hardware that we have access to. And so with like very little code change, just making this small change to work in chunks takes about a third off of your runtime. And so this is the part where we get to look at pseudocode that I doodled. So this is a pretty trivial use of Spark. It gets a lot fancier. There are a lot fancier kind of things that allows you to do in this distributed computing fun stuff. But the simple stuff, which, this is fairly simple, this embarrassingly parallel thing, it makes as simple as you would like it to. So this pseudocode is actually pretty close to the real thing. So we go ahead, we read in our data frame. Map partitions is defined on the RDD backing the data frame, not the data frame itself. If you don't know what that is, that's fine. Don't worry about it. That's the least important thing I have to say out of many unimportant things. But you just have to type .rdd first, and you can call map partitions and just give it an arbitrary Python function, which we are going to define on what I believe is our last slide here. So the Python, it works pretty well with Python. You can do things, so here we are defining a function, we are defining a closure over that random projection that we have fit above. And so within that closure, the interface for map partitions, you define a function that takes an iterator over all of the rows in that particular chunk. So we just exhaust that iterator, put it in a NumPy array, call transform on it, just like we normally do in our scikit-learn land, and then have to turn it back into a list, because unfortunately, so Spark knows how to work with, or PySpark knows how to work with Python lists and Python floats, but doesn't know how to work with NumPy arrays, which unfortunately makes us a bit slower than it needs to. You'll notice we're doing a lot of Python to NumPy to back to Python conversions, and it's maybe even worse, behind the scenes, we might actually even be doing some Java object to Python object conversions. This is actually something that's actively being worked on in Spark. There's some new stuff in 2.3 that makes this a lot better, but not in this particular use case. So it's a source of slowness, but for kind of trivially being able to build distributed processing things that are also fault tolerant, it's pretty neat, and it really is just about this simple. So that's the end. Dimensionality reduction, it's cool. Regularization, it's great. Run some experiments, have fun, transform your big X's using Spark or Dask or whatever. Snakes, thanks, the end.
Okay, we have time for some questions. There's a mic over there, and I'm also holding a mic that I can run to you or walk quickly to you. Oh, sorry. You're right by the light there. Sorry.
Hey, thanks for the talk. This is just something that kind of piqued my interest earlier in your talk. Might just be something I don't know much about, but you talked about how if you have some sort of external covariance in your data, that can be misleading. Dimensionality reduction helps you to avoid that problem. I'm curious, it seems to me if you're reducing dimensions, you're always reducing some amount of information you have. Mm-hmm. It seems like that covariance might be important to look at, to understand, to think about. So what are maybe some of the downsides of eliminating these dimensions? If you eliminate a piece of data that could be important, maybe it's not a spurious covariance, for example. And how would you kind of think about the trade-offs there?
Sure. So the trade-offs would come from, those tables we were looking at, where most of the time when you do this, the trade-off, because you are going to be losing information, and that should lead to reduced AUC. Your models will more than likely get a bit worse. So that's the negative trade-off. So as far as are the correlations spurious or not? So if they are not spurious, so what we're worried about is correlations that would go away if we were to sample more. Those are the things that we are trying to avoid. So our hope is that if it is a true correlation and not just noise that we are observing, not just a problem with our sample set not being big enough, hopefully the real correlations would stick through the reduction. The problem is just that if we have enough variables, something might just happen to correlate just through happenstance. And so that's the kind of thing we're trying to avoid. Does that answer?
Yeah, that's good. And then maybe a follow-up is there any way? Okay, then a quick follow-up. So you mentioned we want to get rid of the ones that are perhaps spurious that would go away if we were to sample more. Fundamentally impossible to tell whether the correlations fall into that category or not, though, correct? So isn't it sort of just we just kind of got to try it? There's not really any theory that would guide whether it's a good idea or not, and you just have to see, it's more predictive, so I guess we'll take it. Is that kind of what it comes down to?
Yeah, exactly.
Okay.
There's not, it kind of has to remain by its nature a hypothesis.
Okay. Cool. All right, that gives me some context. Thank you.
But no, thanks. That's a great question.
Yeah, you mentioned in your talk that dimension reduction will introduce regularizations, and that's what I believe, and it's very interesting. But I must miss did you mention in any result how that manifested itself in your data? Or?
Oh, well, I mean, so the numbers we were looking at were out of sample scores.
Okay.
And like, so we had like, in those examples, we had examples of like transformed and untransformed data, and they were all out of sample. So I'm sorry, so like what else would you suggest looking at?
Oh, I must miss those scores. So you have the scores with regularized?
Yeah, so that was like these tables here.
Yeah.
I mean, are you asking about like, what's the difference between like the difference between like doing this versus like applying an L1 or L2 penalty?
Yeah.
Is that what you're asking?
Yes.
Okay, sure. So I mean, those are kind of aimed at two different things. So if we have, so the problem that I was speaking to was that like there is some correlation due to noise. And so we can, so presumably like no matter how much we bump up our regularization strength, like we would still expect our model to find that correlation. Like we aren't like upset at the model for having picked up like this noise of the data. We're upset at the data for having this noise. So like we would apply like L1 and L2 penalties to try to, bias the results. But like we would presumably not be able to bias it so much that it would ignore a real correlation in our data. It's just that correlation is one that we don't want because we expect it's perhaps noise.
Hey, nice talk. So it's been a while since I used PySpark, since I've used it, and I'm just curious. I know they have a machine learning submodule. Do they have dimensionality reduction features built in?
They do, and and that stuff keeps getting better and better. It's just not quite at like the same. You just don't have like the same richness as you do in scikit-learn.
Sure. Okay.
Yeah.
Thanks.
Sure.
Okay, let's thank our speaker once again.